I'm Ryan, this is Paul, and this is Marcus, and together collectively we are Group 1. Our project this semester was to work on the electronics portion of a student experiment called the Bragg reflection polarimeter. This experiment will be attached to a NASA satellite, hopefully launched in 2014. The main satellite is called GEMS, and its primary purpose is to look at the polarization of various X-ray sources. The BRP's specific interest is from accreting black hole sources. The BRP will observe at 500 electron volts, while the main instrument, called the XPI, will observe between 2 and 10,000 electron volts. The disk of an accreting black hole is hotter the closer to the center of the accretion disk, and the photons there are more energetic. And the strong gravity of the black hole alters the polarization of these energetic photons. And you can see in the charts on the right over there, this is a simulation of black hole data. And the XPI range is in the red area, and our instrument, the BRP, is looking at lower energies. And you can get additional information about the inclination of that accretion disk from these lower energies. On the right, you see a cartoon of where we sit with the main instrument. The box in orange is the detector for the main satellite instrument. In the beam path, in the optical path for that main instrument, is a Bragg reflector, which is where our project gets its name from. This is just a beam splitter. It splits off the lower energy X-rays that we care about while passing through the higher energy X-rays that the main experiment cares about. The red box is our proportional counter, which is the X-ray detector for our experiment, and then the gray box is the electronics that we personally worked on. The incoming radiation from a given source is polarized perpendicular to the direction of travel, and then the spacecraft, this polarization is static then, and the spacecraft rotates around the optical path. And the count rate as you rotate is peaked whenever our reflector is in the same plane as the polarization angle. And this sort of count rate peak as we rotate allows you to discern what the polarization angle is, and then the magnitude of those two peaks is how strongly polarized it is. The BRP electronics is responsible for providing high voltage bias to the detector, as well as recording data that comes from the detector, monitoring housekeeping and basic state of health, and then communicating all of this with the spacecraft. As a basic hardware overview, I was the hardware lead for the project. We have the detector, which is separate from our box. It feeds X-ray data to us. We do some analog processing of that data. We convert it to digital for the microcontroller and then process that and send it on to the spacecraft. So in our power subsystem, we receive a 28-volt main line from the spacecraft. We use an EMI filter and low-voltage power supply pair supplied by Crane Interpoint. The two disks are made to work with each other, and this reduces our noise back into the rest of the system. Our low-voltage power supply gives us a positive and negative 5-volt rail, as well as a common. And we further split those into analog and digital supply rails with some LC filtering that we designed. In the same system, we have a high-voltage power supply. This is responsible for providing bias to the detector. One bias is provided directly around the order of 2,000 volts. And then another bias is divided by 10 with resistors and fed through to the analog system. We also have some passive telemetry in the form of a thermistor on our detector to let us know what the temperature is. And then we've got 2 redundant monitors for the high voltage, as well as that detector temperature, and some basic control for the high voltage through a DAC. In the analog subsystem, as I said before, we receive high voltage from that high voltage supply. We go ahead and split and isolate that into 3 distinct signals. One of them is not instrumented, it's just fed to the detector directly. Another one is instrumented as our event line. An event coming out of the detector is a small amplitude positive current pulse. And so we feed that into a charge-sensitive preamplifier, the A225. Because that's an inverting amplifier, we invert the signal on its output, so we're working with a positive signal again, feed it through a peak hold, and then acquire it with an ADC. The way we know that there's an event to acquire is we also feed it into a comparator, and the output of that comparator triggers an interrupt in our microcontroller. The other instrumented line that I talked about is for anti-coincidence. There are events that get triggered in the detector that are not scientifically relevant for the purposes of this project, and that anti-coincidence lets us take a look at any given event and figure out whether or not we want to record that data. Because we never convert it from analog, it doesn't go through an ADC, we just route it through a comparator and then stretch the signal with a one-shot so the microcontroller can read it. Finally, we have this analog switch here which allows us to provide test pulses to those A225s. That way we know if they're working in the absence of actual events. And we've got some control lines for that test pulsing and for the discriminators that communicate with the microcontroller system. For that microcontroller system, as the name suggests, it's basically the microcontroller. We use an AVR type microcontroller at Mega 128. This microcontroller was chosen because there was some research done on the microcontroller showing it to be resistant to radiation effects, which is important since we're going to be in a radiation environment. We've got 3 DACs that are used for setting the test pulse height for that pulsing circuitry that I talked to you about, as well as 2 of them for the different comparators for our noise discrimination on those event lines. And then we also have the housekeeping from the voltage system, some control lines, and then another passive thermistor inside our electronics box so we can tell the temperature there. Finally, we've got an RS-422 transceiver, which is responsible for our communication with spacecraft.
The instrument firmware was designed based on these requirements. We want events coming into the microcontroller to generate interrupts. We want to capture this information, this event data, and transmit it to the spacecraft. We also want to, at given intervals, collect and transmit housekeeping data related to the health and well-being of the system. And then we also need to receive and decode commands from the spacecraft and acknowledge those. So here's the format of some of the outgoing packets that we send out. Housekeeping packet, which is 22 bytes in length, contains this information here. The event data, this is another packet, and then a command check packet, which is basically what we return to the spacecraft in response to a command that we received. This is a list of commands we can receive from spacecraft. You'll notice that the opcode is formatted in a way such that any single bit error or bit flip won't cause us to go into another command, so it will be easy to recognize invalid commands. We can do such things as enable the high voltage supply, set its level, set discriminator values, reset if we have a broken status. You'll notice that some of these commands actually have 2 arguments, so we may have multiple destinations for these values, and so we can select a destination plus a value for that device. The flowchart for the firmware, we basically start as obviously in an initialization state. We enter the main loop, and then it's basically a series of we check to see has it been long enough that we need to take housekeeping data, collect it, and send it off. If it has, we acquire the data through ADCs and we assemble a packet, and we send this back to spacecraft. If not, we check to see have we received any commands from spacecraft. We decode that command. Based on the command, we perform the appropriate action, and then we format a command check packet, and we send it back to spacecraft. There are a few interrupt vectors that are used in the firmware. The first is in case we have an event and we read from the ADC the height from the peak-hold circuit. After we've acquired that data, we clear or release the peak-hold circuit. We assemble a packet with that data, and we transmit it back, or we send it back to the spacecraft. We use our timer to basically give us an adjustable slew rate on a high voltage power supply. So we're working sometimes with values of 2,000 or 3,000 volts. So this allows us to not change this value instantaneously. At each time rate overflow, we check to see if our set value is different than our real value. We increment it by some finite amount, and then go back into our main loop and check again. And this kind of gives us a slew rate for our high voltage supply.
This diagram is approximately how the spacecraft connects to our own instrument. There's an RS-422 connection that will handle the commands from the spacecraft and the housekeeping telemetry data from our instrument. There's another RS-422 that should handle a pulse per second signal from the spacecraft that we can use for timing purposes, and of course the power from the spacecraft. Now ideally the spacecraft would send the commands to our instrument, which our instrument would respond to. There's this slight issue that the spacecraft itself is not actually available to us, as you can see from this slide. So I was in charge of creating the spacecraft simulator software, which we would use to run and test our instrument while we were still at the University of Iowa. It features a simple GUI for sending commands to the instrument on a serial port, a reasonably accurate pulse per second signal, the ability to graph the housekeeping data and the events that we see, the ability to send relative time sequences of commands, a text display of each packet it receives from the instrument, and the ability to save all of this data to CSV files. This is what I consider the main window. This is from where you can send the commands to the instrument. First of all, there's the little connection section toward the top left of the interface. And below that, you see all the commands that you'd send. Each time you click the send button, it puts that command in a queue that would go to the device. Over a bit to the right of that, you see the relative time sequences. With this, you can basically set a series of commands to be sent in order as soon as you send that relative time sequence. Now, the pulse per second starts as soon as you connect to the device. I'm going to have to be honest that our pulse per second is not handled using the exact same method as on the previous slide, in that we are sending the pulse per second using a set time command over the command line as opposed to using a separate RS-422 line for the pulse per second itself. Now, after each pulse per second is sent, one command is taken from the queue if it is available and sent. This means that this relative time sequence, for instance, would take 3 seconds to run. The graph window is the other major window of our program. It allows you to create the graphs of the data on demand, save the graphs and the packets, and see all the individual packets. You can whether that be the most recent packet or a packet sometime in the past by putting a certain packet number into the show button area. Now, to show a graph, you'd hit one of these buttons that says show voltage supply monitor, for instance, using the one that's closest to me and therefore easier to point to without getting in the way of the image. And you would save it using a button that's right next to it. The graphs look something like this. For the event data, which are those currents that Ryan was talking about earlier, we have a histogram. The event data itself is 1 byte long, so 256 possible values. We just put each of those into a histogram with 256 bins, for simplicity's sake. There's no real count limit on here except for the amount of memory on your computer, so you can run this for quite a while and it will just show a more and more defined wave form for that. Now, the housekeeping data will show up in a line graph. This shows not exactly the time, but the number of packets previous. So on the far right is the most recent packet, 0 packets back, and on the far left, the least recent, 50 packets back. Since the housekeeping rate can be changed via the commands to send once per second or once per 16 seconds or somewhere between, we couldn't really put a second scale on this. Now, this particular graph is of the voltage, so you can see that as soon as it's first turned on, it jumps up a bit, and then when it is set to change up to a higher voltage, in this case 200, it starts to slowly slew up to that value. Now, this is the console for the command, or for the program. Originally, this was not going to be part of the final program. It was just something we were using for debugging, but it was far too useful to get rid of, in my opinion. Basically, with this, you can see the time packets as they are sent to the device. You can see when it receives a device, or when it receives a packet, such as a housekeeping packet or a command check packet from when it would just send a command. So it's very useful for making sure that the device is still working for someone who may be operating our instrument.
All right, so we've given you a lot of information on what it is and what it consists of. But this slide, we're going to show you how it all works, how it gets set up. This is a picture from our lab over at the physics building. You've got Marcus's software here running on the laptop. You've got our power supply box down here with the actual electronics box on its side. And then here we have the prototype detector that the physics group was using for all of their development. In the front, we have a radiation source that's an iron-55 radiation source. Now, the count rate on iron-55 is about 6 kilohertz, and our system is not designed to handle a count rate that high. So we have a high-tech count rate reduction system, tinfoil, in front of our iron-55 source. This is the histogram from one of Marcus's slides. This was actually a histogram of live data. We set the high voltage in the detector to roughly 1.8 kilovolts. We set our event discriminators to about 500 millivolts. The noise floor on this system is a little high. There's definitely future work to reduce that noise floor. And we enable the interrupts inside the system. And you can see here in the histogram that we have a very clear, almost Gaussian peak, which is what data should look like for a given X-ray source. This, with our M slide, is just a picture of what the inside of our electronics box looks like. We've got 2 different boards so that we could independently develop and test out various methods for cleaning up our power supplies. And I'd like to note that those are hand-wound inductors on the power board. Very spiffy. If you have any questions or comments, we'd like to open up the floor to those right now.